So good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petroccione, and I'm the interim director of NITheCS. This afternoon, we are very privileged to have Professor Roger Deane with us. Roger is professor at WITS and also an extraordinary professor at University of Pretoria. I assume he's South African. And he did his PhD in Oxford some 10 years ago. But after that, he returned to South Africa, first at Rhodes University, then at University of Cape Town. In 2018, he moved to the University of Pretoria, where he started the radio astronomy research group. And since a couple of years, he's one of the DSI NRF Sgr A research chairs in radio astronomy at WITS, and he's also the director of the WITS Center for Astrophysics. And today he will share with us some very exciting new results about the black holes at the center of our galaxy, and these are outcomes of the famous Event Horizon Telescope, EHT, not ETH. That's another institution. Yeah? So we are very, very happy, Roger, that you're with us this afternoon, and we are very curious to see and watch what you're going to share with us this afternoon. Yeah? Maybe just for the participants, the usual reminder, please make use of the Q&A facility to ask questions. And at the end of the talk, we will give people the opportunity to raise their hand and ask the question in person. And we will continue today the tradition that we started, I think, a month ago, not to record the questions, so that maybe it's a little bit less intimidating to ask questions in public. Yeah? So, Roger, please, you're welcome to start your presentation. You already see your slide, so you're welcome to start. Thank you very much.
Well, thank you very much, Francesco, and thank you for the very kind introduction and for the invitation. It's very, I think, fitting to share these results with the NITheCS community. I think there are wonderful opportunities within the Event Horizon Telescope and associated science that it enables, that we can interface with the NITheCS community, and I hope to share some of that in the presentation today. Right, so I'm sure anyone here would not have missed this image that you see in the center there of Sagittarius A Star, released on the 12th of May this year. But I'd like to tell you a little bit more about perhaps just the headlines, and get a little bit more into the astrophysics and the physics, and some of the modeling as well that this community may find of interest. So this is, a talk very much on behalf of a lot of work by a lot of people around the world. This is our in-person collaboration meeting back in 2018. After that, unfortunately, we had to meet a lot virtually. And a lot of this work, in fact, that I'm presenting today was done, remotely. These are the various institutes that are affiliated with the Event Horizon Telescope collaboration, and some of the telescopes there. This is a Google map, so you can zoom in via the EHT site if you want to see more detail. And then the big funders of this Event Horizon Telescope that keep the observatories running, that make up the virtual telescope, are these 13 stakeholder institutes, and then affiliate institutes. And of course, South Africa is involved here through WITS, through the University of Pretoria, through Rhodes. And then also South Africa contributes by funding via the National Research Foundation, South African Radio Astronomy Observatory funded postdocs and students, and then of course, myself. So in this talk, I want to start with giving you an overview of black hole shadows, and then talk about the instrument that was assembled and designed to actually make the first images of these predicted shadows. I'll dive into some of the results on Sagittarius A Star itself at the Galactic Center, and then close with some of the exciting times we have ahead in terms of what will be the next generation Event Horizon Telescope, and potentially some of those sites on African soil. I'll talk a little bit about the strategic geographic advantage that we hold here. Now, the primary science goal of this instrument, and very much not an observatory like the square kilometer array aimed at addressing a whole lot of science. In its first instance, it was an experiment, and that was to image the shadow of a black hole. And the roots of black hole shadows go, they go back way back, all the way back to David Hilbert and von Laue, predicting light paths around compact objects. Jim Bardeen did a whole lot of work on looking at a lens star and how that would look behind a black hole, and then also looking at stellar orbits around black holes. Jean-Pierre Luminet did this. This is a numerical simulation that you see on the bottom left here. Back in 1979, quite extraordinary what he could do with a numerical simulation at that point. But what's really interesting, and why we, shows us how spoiled we are these days, the visualization here was done by hand, looking at printouts of the numerical simulation, the results of the numerical simulation, and by hand illustrating this. Then in 2000, Heino Felker and collaborators did this prediction of essentially a ball of plasma around a black hole, and this specific signature. And then in Hollywood, you would have seen more recently Kip Thorne and Christopher Nolan taking some artistic license. There's no Doppler shifting in this, but the shadow feature from Interstellar. Now, a black hole shadow, if you look at the side view to explain it a bit better, there's a distortion of the local space-time due to the exceptionally large mass in a small volume by the black hole. And if you have a thin accretion disk, optically thin in most cases that I'll discuss today, in the red there, you would see the front of the black hole, the accretion disk around the black hole over here. But because of the distortion effects, you would see bending of light over the black hole and under the black hole. And you would see the black hole itself is a central depression here due to the two things really, the bending of light and the capture of light. So those are the two key concepts to understand in trying to understand a black hole shadow. It's the gravitational lensing, the distortion to the local space-time, as well as the fact that there is an event horizon that captures photons that causes this deficit, which you can see in this simulation, where you have photons traveling in the immediate vicinity. Some of them, the closer they get, obviously, the more they appear to be distorted. Some of them orbit around the black hole several times, but photons are captured if they veer too close. And the net result of that is this brightened ring of emission that you see, and then a central depression. And that is the signature that was predicted, and then back in 2019 imaged in M87 star. Now the size of that is roughly, for a Schwarzschild black hole, is about 5 times the gravitational radius. The radius is rather, the diameter of the shadow is about roughly 10 times the gravitational radius. And the spin of the black hole is only about a 10% perturbation on that. So it's really the mass that dominates this. And then that's from retrograde through to prograde spin. There's a complication though, which we spent a lot of time working on, which is mixing in the messy astrophysics and trying to extract that black hole signature, that predicted feature, out of a more messy astrophysical situation where you find black holes. And this is a simulation showing just that. You see the accretion flow in red, plasma orbiting and swirling into the black hole. Sometimes you have jets being launched from the magnetic fields that are twisted in this differential rotation around. And what the Event Horizon Telescope is trying to get at is that the central depression caused by the lensing and the photon capture. So here's just a still of that messy astrophysical situation, the accretion disk, the accretion flow falling into the black hole, but a clear shadow feature in its center, where you have a photon ring. You have the event horizon, which is in real terms a lot smaller, but the photon ring is lensed to be larger. But you have all sorts of emission in front and behind the black hole, which can complicate this feature. But nonetheless, this is the prediction that was made back by Heino Felker and collaborators in 2000. And in that paper, they said millimeter VLBI, very long baseline interferometry, antennas spread across the Earth, would have the achievable angular resolution to potentially see this feature. And that was one of the key key drivers behind assembling the Event Horizon Telescope, which in itself was, absolutely no mean feat. I'm a relatively new member of the Event Horizon Telescope collaboration. I've only been part of it for about 7 years. There are people that have dedicated almost their entire careers, many decades, to assembling this telescope, which is just an incredible instrument. I mean, you can see some example stations here on the right, but essentially it's a network of antennas spread across the globe that need to observe the same source at the same time, and record data at these different sites, and it's that network that is able to image black hole shadows. So this is ALMA in Chile, the Sgr A of the millimeter world. This is on top of a 5,000 meter volcano in Hawaii, and this is at the South Pole. You can see the bicep experiment there, and sorry, that's active bicep, and you can see, sorry, not act, bicep, and the South Pole telescope up here, 15 meter. So for those not familiar with interferometry, the Event Horizon Telescope is absolutely not a point and shoot instrument in the slightest. Unfortunately, I use the Very Large Array, the current the centimeter wave radio interferometer in New Mexico in the United States, just to illustrate some of the points of radio interferometry. But the way to think about this is not individual antennas, but rather pairs of antennas. So think of this, we call these baselines, and each pair will measure per unit time and per unit frequency a cross correlation of the sky brightness distribution. So this is a 2D Fourier transform machine effectively, and there are many handshakes. If n is the number of antennas, n times n minus 1 over 2. You can see for this array, you can't see all the antennas here, but there are 27 of them. So there are 351 handshakes happening per unit time, per unit frequency. In South Africa, we have Meerkat, which goes up to 2,000 baselines. And then you can see the data explosion as we go to the Sgr A. Now, the EHT only has, well, in 2017, the results that I'm showing today, 8 antennas, different stations at 6 different geographical sites. So they're 28 baselines. So we're starved for these samples of the 2D Fourier transform of the sky. The other key thing here is that the largest separation between antennas in a given interferometer is what determines, the sharpest possible feature that you might see in the image that you produce. So the angular resolution is dictated by the observing wavelength and the largest separation. And in the EHT case, that is 20 micro arc seconds. Contrast with Meerkat, which is more like 10 arc seconds. So about a factor of 1 million difference. Now, if I just can say 1 or 2 things about radio interferometry, the actual the measurement equation, as we refer to it, just for the purposes of showcasing some of the, or coming back to some of the Bayesian inference and modeling that is done on the EHT data. So we measure with radio interferometers quantities called visibilities. They are complex quantities. So this is the visibility as measured between antenna P and antenna Q, making baseline PQ. We arrange them in these 2x2 matrices because it's pretty convenient from a polarized.
Sorry, am I the only one who can't hear Roger at the moment?
No, me too.
Okay. I'm not sure what happened.
Let's give him a few minutes.
No. This is the time that load shedding starts, I think. Oh, let me check. Yeah, I think 4 o'clock was the time that load shedding started. Let's wait a second and see if Roger can join us again. Let me see. Yeah, please be patient with us. This is beyond our control. Let's see if he sent us a message. Not yet. Okay, I'm sure he's making a plan to come back online. Here we go. Hi, Roger. Are you back?
Yes, I'm back. Sorry about that.
No problem. It's probably the load shedding. Huh?
I think so. I think there might have been a switch of power that I didn't notice. Anyway, I'm on my mobile connection now, so this should work fine.
Okay, perfect. Thank you very much.
Where was I booted out? What did I say about this slide? Had I started on this slide?
You started, I think you said something when the first element of the covariance matrix was, yes, kind of highlighted.
Okay,
yeah.
All right. So this is how we, for convenience, we put this in a 2x2 matrix, and visibility is these complex quantities that have an amplitude and a phase, or a real and imaginary component. We sort them in this way for convenience. And then we have what we call the radiointerferometry measurement equation, where we have the source coherency matrix, which is basically just the properties of the source in the Fourier domain. And then we have what we call instrumental gains. These are corruptions that you can think of this as an onion shell, where you can incorporate a whole range of different possible corrupting effects, from the deformations of the antennas to atmospheric effects, tropospheric effects. The point is that we put this all together and we're able to jointly model observations, both the source parameters and the instrumental parameters. And I'll come back to that a bit later. But yeah, a radiointerferometer is a Fourier transform machine, and this is a building at the University of Pretoria, where you see regularly spaced features. This is the 2D Fourier transform of that building. In radiointerferometry, we only measure a small part of that due to limited number of antennas and limited angular resolution, but you're still able to recover generic features of that image. And as you increase the sampling, so your recovered image will get closer and closer to the real image. So this is what we do. We have baselines, antenna P and antenna Q across the Earth. And as we do that, as the Earth rotates and we make measurements with these baselines, we slowly start to sample parts of the 2D Fourier transform of whatever we are looking at. Another way of looking at the visibilities, remember I said they're complex quantities, the amplitude can give you a sense of what you're looking at. And in this case, we're plotting the visibility amplitudes as a distance, as a function of the baseline length. And if this were a point source that were over here, a Dirac delta, you would just see a straight line. You would see the same amount of power or brightness regardless of how long the baseline length is. If it were a Gaussian, well, the Fourier transform of a Gaussian is a Gaussian, you would just see a drop off as a Gaussian. But because this is a ring-like structure, you see a bounce. That's the Fourier transform of a ring. Now, some of the challenges we face with using the Event Horizon Telescope, we're forced to go to very high frequencies because we need the maximum possible angular resolution. So where the Sgr A will observe in this fairly well-behaved part of the atmosphere, the EHT is forced to go to 1 millimeter, and the opacity there at sea level is close to 100% for these observations. So we need to go to high mountains. Another reason we have to do that is because of the turbulence that is present in the precipitable water vapor in the atmosphere. And what that does is it induces additional and time variable path lengths to incoming radiation at 1 millimeter. You have Kolmogorov turbulence that basically means that over a time scale of a few seconds, you have phase changes of the incoming wavefront or distortions to it greater than a radian, and that's the definition of the coherence time. So we also have data challenges. These are some of the disk packs that arrived at the correlator. That's that supercomputer that basically combines the signals from each of these. About 4 terabytes are required in 2017. This is almost this has doubled since in our Lotus campaign, and it will increase dramatically over the next while. Remember that in n times n-1 scaling as you add additional stations. And on Sagittarius Star alone, it's just 0.5 terabytes. It's quite interesting to collect so much data and then make an image that is just a few kilobytes, but that's the way it is. And then also what's interesting is that, at each of these stations, this is Pico Veleta in Spain, sensing the electric field in the direction of the target, but that needs to be captured by a digital backend. And a key component of that is some of the Meerkat and Sgr A technology developed right here in South Africa, the so-called Roach 2 boards, 4 of them at each digital backend. That'll have to increase now as we increase our bandwidth as well. But just an aside on how South African technology is already contributing to the EHT. So we have these stations that collect data. We record these disk packs. Some of them have to, like the South Pole, have to wait for winter, to the end of winter before they can be put on planes and sent to one central facility called the EHT correlator. There we make as if the signals all arrive at the exact same time, and they are that cross multiplication with the conjugate of antenna P and antenna Q in the whole array is performed. That the timing of that is not perfect, so there are some corrections that need to be done to the applied delays, and then there is some a priori calibration and self-calibration, and then image reconstruction. So in essence, the EHT is this global array of antennas trying to image, orbiting plasma around a black hole far away with the angular resolution that's equivalent to the size of a donut on the moon. And our 2 primary targets are the center of M87, a 6 billion solar mass black hole. And that was released, the image of that was released back in 2019. And the subject of today's talk and the recent press release, which was at the center of our own Milky Way, a disk-like galaxy, far closer, 27,000 light years. All right, so imaging the center of the black hole at the center of our galaxy is a challenge because we live in, there are additional challenges compared to M87, because we live in this disk-like galaxy. And also in contrast to M87, a lot of our stations are in the northern hemisphere, whereas the galactic black hole is in the southern sky. So that produced additional challenges. But if we go down to it, we have these stations that are good to a few hundred micron in the RMS sensitivity, looking up at the center of our galaxy, which you can see this beautiful Meerkat image of, is a complex place. And right at the center of this very complex image lies those famous S2 stars orbiting the central black hole, winner of the Nobel Prize back in 2020. And if you zoom in by a factor of a few thousand, this is the image that was released of Sagittarius A star with the Event Horizon Telescope at 230 gigahertz. We had a number of press releases. One was in the planetarium, which we're upgrading here at WITS. But essentially, you're looking at a ring-like feature that is around 52 microarc seconds across. Really, really remarkably similar to those predictions made more than 2 decades ago on what this might look like, and that millimeter VLBI might be able to capture it. I want to emphasize that there isn't just one image. The press sort of brings out one image, but there are many, many images because of our sparse sampling that are consistent with the data, with those visibilities that are actually recorded by the different baselines. But overwhelmingly, the overwhelming majority of images that are consistent with the data have ring-like morphologies. There's a very small fraction here you can see that doesn't look anything like a ring, whereas the vast majority of these, using 4 different imaging algorithms, reconstructing images on multiple different subsets of the data, we're able to make images on short timescales because Sagittarius A star is extremely bright at 1.3 millimeters. There are also 2 different observing days with different UV coverage. And just to, we've made the data public, both for M87 and Sagittarius A star will be public. And this has been independently verified, these techniques with independent experts around the world. So this was our Fourier coverage on the 2 days, Sagittarius A star, April 6th, 2017, and April 7th. And you can see closer into the origin is larger features. So we don't have great coverage for larger features, which is important for our imaging fidelity. And then further out, you can see 25 microarc second spatial frequencies out here. Going back to that plot of amplitude against baseline length, you can immediately just see in the not quite raw data, but before what we call self-calibration, you can see this sort of bouncing like effect. And what's in the dashed line here is a 50 microarc second, 54 microarc second ring, smoothed by Gaussian to be able to see just by eye. This is just to illustrate the qualitative appearance of a ring here. It's quite interesting to contrast M87, the image that was produced back in 2019, to the Sagittarius A star image. They look about the same size in the sky, within a factor of 20%, but in spatial terms, M87, if you remember the XKCD cartoon, encapsulates our entire solar system, whereas Sagittarius A star is more consistent. It fits within Mercury's orbit. So they're very, very different sized black holes, about 1,600 times different in mass. And the result of that means that Sagittarius A star orbits around Sagittarius A star on the time scale of minutes, depending on what the spin is. Whereas with M87, it's several months. So think of trying to take a long exposure photograph of some kids running around at a rapid rate. It's a lot harder than someone sitting for a portrait, and that's part of the analogy of the difference between M87 and Sagittarius A star. The other one is that sitting inside of our Milky Way galaxy and looking directly in the plane towards the center of the galaxy, we have to look through quite a large column density of free electrons, and they serve to scatter the image considerably. This is why with galactic pulsars and fast radio bursts, one has to de-disperse the data to correct for the delays as a result of those free electrons. Here you have to do it, but you have to do it as a function of distance, position in the image, especially with the refractive scattering. So that's an additional complication by virtue of Sagittarius A star sitting in the center of our galaxy. It's a complex place, as I said. This is this beautiful image from Meerkat with Sagittarius A star right in the center there. But there's an additional complexity. Right in the center there lies this point source, which is Sagittarius A star. And you see the famous mini spiral here. And on the timescale of hours, pay attention to the x-axis here, you're seeing rapid time variation of the source. You can see it dimming, brightening again, and then dimming. Now, this is an enormous challenge for interferometry because it basically violates one of the fundamental assumptions of the radio interferometry measurement equation, which is that the sky is static. So that's part of the reason this was a lot harder than M87, and a whole lot of new techniques needed to be taken into account, because not only is this point source varying, and that had to be removed from the data prior to self-calibration, but on top of that, you have image plane variation as a function of location in this image due to the scattering and then the intrinsic variability around the source. So there were a whole lot of very interesting weighting schemes that needed to be kind of built up effectively to account for this additional source of uncertainty and due to the variability. All right, so let me take you a little bit through the NITheCS community will likely be interested in the parameter estimation and model selection. So we obviously have to understand our data, we need to compare with some well-founded models. These all start with black hole simulations, general relativistic magnetohydrodynamical simulations of the black hole environment. And you see a few examples here. And you also see a few magnetic field lines illustrated in these black hole images. And the two primary flavors are called so-called sane and mad, with two different spins there, dimensionless spin parameter of the black hole, where you have essentially the difference between mad and sane are the configuration of the magnetic field. Mad is you can think of it as a much hotter, more concentrated, dense magnetic field environment and dynamically important magnetic field configuration than the same. And our models are tending to be favoring these at this stage. So then you have those black hole simulations, but then of course you have to ray trace them around the black hole to see the shadow-like feature. And what this video shows is a library of black holes with additional parameters on things like the electron to proton temperature ratio. You obviously have position angle effects. And then what slowly happens is you can see the morphological features here. And as you start to compare with certain observed properties, you can start to rule out some of these in the library that you produce. It's obviously very expensive to produce a large suite of Sgr A MHD libraries, but this is what you can do. And then in addition to that, you start to compare with external features, extra information that's not from the EHD observations, but things like the X-ray luminosity, the lower frequency, radio frequency appearance. These sorts of things start to allow you to exclude some of these models and at least qualitatively say, well, you know, these data are more consistent with these kinds of models. Just an aside, this lends itself very nicely to a very an unsupervised learning application. And a recently graduated master's student of mine, Michaela Benegaldo, took to this by taking 100,000 of these black hole simulated images and just using a self-organizing map to classify them from 100,000 down to 64 representative images in a lattice. And what's encoded here is obviously size. You can see size, but you can also see things like the electron ion temperature ratio appearing in different parts of the map. That tends to have puffier shadows if the electrons are hotter. Now, what's important is then to take those Sgr A MHD perfect idealized movies and snapshots, which you see here, and then say, all right, well, I have this imperfect telescope and I have realistic conditions on the ground, in the atmosphere, and between us and the galactic center. How does that impact my observations? So you need to average them on some time scale and then put them through as accurately as you understand the instrument to behave and the optics to try and see, okay, well, what would that actually look like? So that you're comparing apples with apples when you're performing your Bayesian inference. And postdoc here at WITS, Dr. Natarayan has been a key person in this endeavor, doing some fantastic work. Coincidentally, the two of us are the only EHD collaboration members, and we certainly hope to expand that in the future. There are a whole range of models. Something that was developed was the so-called MG rings, where you have Fourier components along annually, where you can describe different profile, and depending on the order, the M order, you can add more and more azimuth or complexity to this, as well as get out physically interesting parameters of the black hole, like the diameter or the width. And this was done in the image plane for a whole range of different methods for these different parameters. So you can look at the diameter of the ring of order just over 50 microarc seconds using different, I know there's a lot taken in the slide, but I just want to emphasize redundancy, different calibration pipelines of the visibilities, different ways of extracting diameters, different imaging algorithms used here. So, very much the motto, because the EHD was doing something so different and breaking new ground, was redundancy on all fronts. And then if you look at the model selection, increasing complexity, you can see the number of parameters in models here increasing. And this is the log likelihood on the y-axis. And you can see as you obviously add more parameters, this gets higher and higher likelihood. If you zoom in on this, the circles versus the crosses, the circles are the ring-like models, geometric models, whereas crosses are not. And you can see clearly outperforming these for comparable number of parameters by many tens to hundreds of in log likelihood are these ring-like morphologies. So not just by eye, but by Bayesian model selection as well. Once you've measured those diameters from the actual image, you have to calibrate that then into a gravitational scale, a physical scale, because just because you have the light showing up in that immediate vicinity, it doesn't mean that captures the diameter, of course. Now, there are prizes on this from this Nobel Prize winning work of monitoring stars of Sagittarius, going around Sagittarius A Star, and the posteriors of the gravitational scale, the mass of the black hole divided by the distance to the black hole, m over d. You can see the posteriors here from Keck and VLT. You can see differences in those, that are small. Those systematics are smaller than their quoted random errors. But it turns out that our random errors are larger than the systematic, so we don't need to pay too much attention to that yet. But if we compare that, you can see the Keck and VLT posteriors of the 68 confidence levels, here on these two vertical bands, and you can see the posteriors from the images using a range of different techniques, also all within 68% confidence intervals of that, using a range of different techniques that include all the data or snapshots of the data, image only versus full visibility modeling. So this is all consistent with what has been measured. Now, you can do a whole range of things. This is not necessarily my area of expertise, but I thought of interest would be just immediately the morphology. Can start to say a few things and let me start to exclude certain alternatives to to whether or not there might be a black hole. You can start to address questions like, is there an event horizon or some kind of reflective surface? If you parameterize the albedo of that reflective surface, you change the morphology, and that's what the paper 16 did here, exploring that. So immediately you can start to put constraints on what the albedo of a reflective surface is if it's present, and there are constraints on that as well. That obviously coupled with near infrared and X-ray luminosities. That's why it's really important that M87 campaigns, which are carried out annually, are performed in concert with multi-wavelength observatories, and some of my colleagues here at WITS obviously working very, very much with Hess. Hess is involved, but you can see a slew of observatories across the electromagnetic spectrum assisting these observations. Then I'm sure there are experts in the room far superior to me talking about looking at gravitational tests, but the EHT adds a contribution to the list of tests of gravity. So if you look at the gravitational potential and curvature space, it sits in a unique part of that parameter space. Here, similar potentials, obviously, to LIGO and Virgo, but much smaller curvature. So there are a whole range of tests that can be done here, and that will only improve as we add more and more stations to the array. But it's wonderful to see 8 orders of magnitude in black hole mass and tests on deviations from Kerr on this being performed on very, very different black holes, and so far at least confirming the scale-free nature of GR working here. So let me close out with just talking about the future a little bit and exciting times. And I think we're South African observers and theorists can come together in this what is really just the opening of this new endeavor of black hole imaging. So what you can see here in yellow are the 2017 stations. In orange are the stations that have been added subsequently and have participated in previous campaigns. And then in cyan are some proposed stations with the next generation EHT. You can see it's mostly in North America and South America, but there is currently an idea to put a station in Namibia. Now, this improves, just every additional station makes remarkable improvement to the imaging quality. So you can see a simulation here of an M87-like black hole, where it's not just a shadow, but you can see the base of the jet, which is critically important not only for connecting black holes as the engines of these relativistic large-scale jets that we see emanating from them, but also to help calibrate and improve the dynamic range of the images themselves. The interferometer is blind to some of this emission, but if you add lots of short spacings and you couple it together, you improve the images as a whole. So that's really, really important. And you can see how this is what we would be able to recover of that image, that simulated image from 2017. If we add the NGHT stations, which I've just shown, you get a remarkably improved image and much higher dynamic range, much sharper shadow, and far more improved tests of gravity. Doing this in full Stokes, I haven't talked about polarization today. There's just simply too much to talk about. But this is becoming an increasingly large focus within the HT, doing some incredible tests of accretion flows and the importance of magnetic fields in that accretion flow. And then what's extremely exciting is, the world of transient astrophysics has really become remarkable. And Sagittarius A Star is a transient factory. I mean, the region in the galactic center is certainly, but Sagittarius A Star as well. So, the more you do concerted campaigns on that central source, the more likely you are to see blobs of plasma orbiting around, and the far superior, interesting relativistic tests that come with that. So science with the HT, as it becomes the NGHT, becomes far more from just trying to image black holes to a much larger portfolio of very, very exciting science, including those tests of gravity and understanding jet launch from black holes, but also searching for binary supermassive black holes and actually monitoring the orbits of those binaries. That's in fact how I got involved in the HT right in the beginning. Searches for pulsars at the galactic center. You can do this at high frequency where the scattering is not as bad. And then, of course, transient sources and a whole range of multi-wavelength analyses. So this is, of course, a lot of overlap with the square kilometer array. And, we have a lot of expertise, theoretical and observational, in South Africa to contribute towards this. Now, what we're really trying to do is to make this network expand onto the African continent, because especially in the case of Sagittarius A Star, there is a strong geographic advantage towards looking at this region of sky in the southern hemisphere. One of the reasons this meerkat image is such a high quality is because Sagittarius A Star passes directly above us here in South Africa. And what we hope to do is turn black hole images into movies. So what you're seeing here is a simulation by Michael Johnson from Harvard, basically looking at 4 additional African stations, and the remarkable improvement that makes to the imaging, the snapshot imaging quality. So look at the timescales here, looking at hours, minutes, seconds. This is a real-time test of gravity that you're able to make substantial contributions to, transformative contributions to, if you place stations in multiple stations in the southern hemisphere. So the first, as I mentioned, Namibia, 2,300 meters. I was fortunate to go up to that. Also quite scary. This is definitely the scariest 4x4 ride you'll ever have. But the plan is to get the 15-meter CEST dish, which is decommissioned and sitting in Chile, moved up to the top of that mountain. And we're hoping that gets funded quite soon. South Africa's made quite a lot of contributions towards that effort, both in providing the framework to simulate it. There's a student co-funded by that, and getting a radiometer on top of there. And what we're also looking at is a smaller dish. 15 meters is quite large in the millimeter world, but looking at a much smaller dish at a well-established South African site to contribute to this effort. The more nodes you add, the far superior imaging you have, and especially if you have a node that's quite isolated like Namibia, it becomes very important to have a second station there for calibration purposes. So there are a whole range of possibilities here where we could put in a very low cost, sort of 6 to 8 meter dish at a well-established site like Sutherland, for example, where we can become part of this global collaboration and make very, very substantive contributions. We're not sensitivity starved. We are UV coverage starved. So even small dishes can make really, really large contributions. And as you saw with those African stations, they really enable the movies because you get the UV coverage in the east-west direction, especially with ALMA. And then what's really nice is the contribution that this short baseline, we just put Sutherland here for as an example station in South Africa, that this short baseline is actually really important. It corresponds to that line there, the north-south. And remember, one of our key science goals is really to try and tie the black hole shadow and that region of jet launch to the larger scale jets. That really, really is important for a lot of our science goals, and this baseline will be important in that endeavor. But on top of that, the African stations would add some of the longest baselines, and then also this continuous coverage with ALMA that is incredibly important. So yeah, we're looking at this. There's lots of synergy with the square kilometer array, both from a technological and a scientific perspective, but also from a human perspective in terms of skills. This is a bit of detail, but we're going to low sites here rather than like Sutherland, rather than 5,000 meter volcanoes, because new technology is allowing us to do that, which ultimately means that we can build these things far cheaper, because we effectively have adaptive optics systems for millimeter, the equivalent of optical near-infrared adaptive optics for millimeter single dish radio telescopes. So that really is an exciting part of the future. So what Inian and I were trying to do in this article is just really kind of emphasize that the only reason we're involved in the EHG in the first place was leveraging off investments made towards MeerKAT and the square kilometer array and some of the techniques there, and trying to encourage us to think about beyond just Sgr A. There are a whole lot of really exciting experiments for our community, theoretical and observational, that we have expertise in and can contribute towards. We have the Sgr A, but the Sgr A will be part of global networks called very long baseline interferometry networks. This will be the centimeter wave in the orange here. This was from a meeting that I was on the SOC of earlier this year. There will be a low frequency network centered on the Australian Sgr A low site, but there will also be an Sgr A high site centered in New Mexico called the NGVLA. So very long baseline interferometry using these Earth-sized telescopes is really a prominent feature on the future horizon of astronomy, and it's an exciting time to do a whole range of very interesting physics. And I'll just close with just sort of talking about the wisdom. Our Vice Chancellor Zebulon Vilakazi spoke of the importance of the cyclotron as a test bed and performing a lot of important work here in South Africa, but putting us in the game in terms of leading contributions towards the LHC. Some of the leaders of the Square Kilometer Array project and the MeerKAT project, Rob Adam, Justin Jonas, and Bernie Fanneroff, Khotso Mokhele, they saw the same thing. With Cat 20 and Cat 7, build it and they'll come, build it and you build the expertise. And I think the same is true of very long baseline interferometry, an exciting future. And EHT is a very high profile example of that, where we can, really build some expertise and play a leading role in this Sgr A era. So that's my summary. EHT has achieved its primary goals of imaging black hole shadows of these two targets, but it really is, I hope I've convinced you that it's just getting started. There's a whole range of new endeavors with new sites, higher frequency, larger bandwidths, higher imaging fidelity. And, a lot of the work has gone into just the algorithm development, the engineering, and now the focus can shift a bit more to enhancing the science cases even further. The black hole masses, as I said, consistent with stellar dynamics, previously derived. The ring diameter and shapes are consistent with Kerr for the moment within the imaging uncertainties. And the tests of Sgr A are now across 3 orders of magnitude. And just to close with, the expansion really is an exciting time. And I think for this community, this could be a wonderful research endeavor within the portfolio to do some exciting cutting edge research in the future. So with that, I will say thank you and take questions.
Yeah, thank you very much, Roger, for a fascinating talk. Thank you very much.